So we're going to plug in the guess. And if we were to do that, we would find that it is good if these things are true. These are the equations that would fall out if you plugged the guess in. A would be equal to Q initial. The initial value of charge that we were to build up with some initial condition, A would be that value. B would be R over 2L, and that's basically the damping rate. So just like we thought in that part of the equation, B looked like the damping part. That's the value, R over 2L. And then C, and here's something that happens in physics. There are two C's, right? So here, C is the capacitance of this circuit. But in the answer, C was one of the parameters we stuck in the answer. We only have so many letters. It happens. You have to get it out of context. Sometimes it's hard. I didn't mean to do something this bad, though. C is the square root of 1 over LC minus R over 2L squared. And that is the reduced frequency, or it has a lot of names. What that's telling you is you'll have some initial charge, the motion will be damped, and it will be an oscillation. This is the frequency of the oscillation. Remember, the square root of 1 over LC was the frequency of just a pure LC circuit. When you add resistance in, what it does is it oscillates at a lower frequency. It's the reduced frequency. Sometimes it's called omega D for damped frequency instead of omega naught for just the square root of 1 over LC. And here's that evil thing I did. This is the capacitance, and this is that parameter C. I put two C's in one equation. Normally I wouldn't do that to you. I'm trying to demonstrate what can happen in a lecture. So you got to be ready. You got to be ready to get it from context. If you see a C right next to an L, you know that means the capacitance. If I'm laying out the values in this equation of the previous guess, A, B, C, you know that's the C in the guess. Sometimes it happens, you got to go with the flow. Okay, so if we put all that together, it would look something like this. I don't want to mess this up. Q as a function of time would be Q max, or Q init is what I called it. You could call it Q max as well because it's the highest charge you'll get. E to the minus R over 2LT cosine the square root of 1 over LC minus R over 2L squared T. So that's your full mathematical solution. So we made a guess that looked a lot like that. Now we've plugged it in and solved for the three parameters. So now let's plot it. Let's look and see what would it really look like. Let's see. Now this would be Q as a function of time, and we have a time axis like that, and it's going to start at some Q initial, or you might call it Q max, and it's going to oscillate and decay. So it's going to do something like this, like that. So you can see the oscillation very clearly. That's the cosine. And if you were to think about an envelope going around the amplitude of this oscillation, the envelope is like an exponential decay. So we could say this is the decay, this is the oscillation, and they happen together in an RLC circuit. Let's see, I could demonstrate this for you, but I already did. If you think back to when we demonstrated the LC circuit, the answer we derived was an oscillation, a sinusoid that sort of just went on forever. But if you look closely at the actual behavior that I showed you on the screen, you could see that it was going down. And that's because the real LC circuit I demonstrated had resistance in it. The wires have resistance. It's low, but it's not zero. And the inductor has a huge number of turns inside that inductor. That's a lot of wire, a lot of really thin wire, and therefore a reasonable amount of resistance that's hard to get rid of. So anytime you demo an LC circuit, you usually, well, you're always demoing really an RLC circuit. So you always have some level of damping in the circuit.